All right, last class, we were talking about the quantum hotel, a place where electrons can go to stay. And this is an analogy for our principal quantum number, n, our subshells, s, p, d, f, and the orbitals within those subshells, which are the shapes. So we had the sphere, we had p has the peanuts or the dumbbells. So there's 3 of those. D has the double dumbbells. Let's go back and look at those so we can see them. The double dumbbells plus the one with the donut. So the 5 different shapes, these are each individual orbitals within the D subshell. So subshell is D, and these are each individual orbitals. We don't really separate or specify individual orbitals in this class. That's something that you would do more towards your upper level undergraduate classes if you do a chemistry major. And there was also F, and we don't look at that or really even talk about it because it's scary. So within each of those orbitals, within each of those shapes, we can fit 2 electrons. And 2 rules for the ways that we can fit those electrons in. Our first rule, let's go back to it, the Pauli exclusion principle. An orbital, a specific shape, can hold no more than 2 electrons, and they have to have opposing spin. So when we're drawing in our orbital diagrams, we can have one of our electrons with upspin, the other one must have downspin if we have 2 electrons. And that's for each of these little boxes in our orbital diagram. They can't be matching either up or down, and we can't fit 3 electrons in either. Also, the options are only up and down, so you can't have like left or right spin. And then we also had Hund's rule. And so Hund's rule says that when we're filling orbitals of equal energy, so if we're filling in, for example, our 2p, anything that's p, d, or f, we'll just be doing p and d stuff. We'll have 3 or 5 boxes, and these are, the formal term is degenerate. That's the actual term. It just means that they're of equal energy level. But I think it's fun that it's called degenerate. So they're equal energy level, and so when we're filling in these energy levels, they're all the same. This is like you walk into a hotel room and there's 3 beds as your options. It doesn't really matter which one you pick. You just go and pick one of them. You're probably not going to fight with somebody unless you're a very particular kind of person. So you would just go and pick any of the beds, and you're going to pick a bed, right? So with this orbital diagram example, we filled in one of the beds. Then we filled in just the second bed because it was the next thing. It would have been just fine if we had filled in this last bed instead of the middle bed. And then if we had one more person, we would fill in all 3 of the beds with 1 person each, and then we would start to double up. This is also how we would fill in beds probably if we were staying with friends at a hotel. So that's like our real fast, rough overview of everything that we learned last class with all of that. And you may remember that we saw this energy diagram previously. So we've got all of our S subshell, all of our P subshells, all of our D subshells, and we're increasing in energy as we go from bottom to top. So when we're filling in electrons for ground state, so our lowest energy configuration, when we're filling them in, we start filling them in from the bottom, and then we fill in the next highest level after that. And it starts off in a way that makes sense. It starts off with 1s, that's our lowest energy. Our n equals 1 principal quantum number, principal quantum shell, our principal shell, just has one of our subshells, one of our letters, S. In 2, we unlock our second, so we unlock P. So 2s fills in first, then we go to 2p, then we move up to 3, because that's all of the stuff that we've got for our n equals 2. So in 3, we fill in our S, because that's our sphere, it's our lowest energy. Then we go to our peanuts, or our double dumbbells, our dumbbells, single dumbbells. And then we would expect maybe that we would jump to 3D, and unfortunately that is not the way that it works. So we would jump up to 4s. And this seems confusing. There are a couple of tools that we can use to remember this energy filling diagram other than just memorizing this. But I think that's the least easy way to do it. Okay, so one of the energy filling, orbital filling order tools that we can use is this one. And so the way that this one works is we've got all of our S subshells in this column. We've got all of our P subshells in this column. Then we've got D, then we've got F. So subshell is our headers or our columns. And then going down, that's confusing. Going down, we've got our N. So we've got options for, my pen will work, 1, 2, 3, 4, 5, etc. So we're making basically a grid. You can think of like if you had a spreadsheet or something, we were filling these in. For our n equals 1, the only subshell, the only letter that we have is S, so we don't put anything into 1p. For 2, n equals 2, we've got S and P. In 3, that's when we unlock D, so we've got 3S, 3P, 3D. And once we've filled out that layout, then we read across at a diagonal. So moving from the top right to the bottom left, that's what all these arrows are for. So we'd fill in 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S, etc., etc., etc. So this is kind of a cool tool. There's an easier way, though. I think this is fun. This is cool. But the easier way is to just read off of our periodic table. But this tool works. It gets you the correct order. I think the periodic table works better, is more fun. So to be able to fill in orbitals from the periodic table, we need to learn some areas. There's some zones, some regions. So our zones are the S block, which is our alkali and alkaline earth metals. It also includes helium. We've got our P block, which is everything that's in green over here. So from boron over to neon and everything below them, that's all the P block. Our D block lives in the middle. So that's all of our transition metals. And then our very scary F block is the lanthanides and actinides that usually gets pulled out and set below the periodic table. We don't touch the F block in this class, not even with a 10-foot pole. We just look at it from afar. So our zones are blocks to know. These are blocks that I suggest memorizing. Memorize these blocks. We've got our S block on the left. We've got our P block on the right. We've got our D block in the middle. And they all go in the square hole. So those are our S, P, and D blocks. Again, we don't really touch the F blocks. And I'll show you how to do that filling in, so don't worry, we haven't missed it. My slides are just in an order. Somebody put them in this order. Who did that? Okay, so a summary of just some of the stuff we learned so far. Lower energy orbitals will fill before our higher energy orbitals. So for example, 1s fills before 2s. Those are our two lowest energy orbitals. The orbitals, the shapes, can hold no more than 2 electrons each. And when there's 2 in the same orbital, the same box, the same shape, they have to have opposing spins. So up and down, for example. If we've got orbitals of identical energy, P or D subshells would have these. So like 3P. If we've got equal energy, then we need to fill them in singly first. And then after that, we can start to fill them in doubled up. This is, you can fill them in whatever order you want as long as you get to the correct end destination. So you could fill it in up, down, up, up. You don't have to like actually physically write them in the up, 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 and then fill in down, just as long as the end result is correct. So this would be an example of one that's good. An example of one that would be bad would be if we had up, down, up, down. And the reason this one's bad is because we've got an empty orbital. So one of these two orbitals should split up and share between the two orbitals instead. Any questions about gestures at the board? Cool. Okay, let's do some electron configurations for nitrogen, oxygen, fluorine, and neon. I'll get us started with nitrogen. So for nitrogen, we're looking at our periodic table. We're going to hone in on N for nitrogen. It's in our second row. It's over in our P block. It's the third entry in our P block. And it's got a number of 7 up in the top right corner. So symbol for nitrogen is N. Nitrogen has 7 electrons. And so its electron configuration, we've got 1s as our lowest energy orbital. And we can put 2 electrons into our 1s. So that fills it up. Because we just have the one shape, just the one sphere shape. We've got one place to put electrons. We can put 2 total in 1s. After 1s comes 2s, and that one also can be filled up. And after we do that, we'll have 3 remaining electrons. So after 1s and 2s, we've allocated 4 of our 7 electrons. 7 minus 4 gives us 3 remaining electrons. After 2s comes 2p. So we get 2p, we've got 3 electrons left. We can place all 3 of them into our 2p. And then for our orbital diagram, it's the same idea as our electron configuration, but we're representing it with up arrows and down arrows. So we've got our 1s, our 2s, and for our 2p, we've got now 3 boxes. 3 boxes because we've got 3 of the shapes. So we've got the 3 different peanut shapes or dumbbell shapes. And for filling in those electrons for 1s and 2s, they're both up and down. And then for 2p, we're filling in 3 electrons. We've got 3 boxes. We're going to fill them in 1, 2, 3. So we'll have matching up spin for all 3 of our electrons. So go ahead and fill out for oxygen, fluorine, and neon. For each of those, we're just adding 1 electron. So you can kind of just copy paste the electron configuration orbital diagram and just add 1 electron and just see what those look like. All right, that was a little bit of time, maybe not enough for you to get all of them drawn in. But for the sake of time, we're going to keep moving. Okay, so we are moving on from nitrogen to oxygen. So oxygen has 8 electrons. All right, we've just added 1 electron, and so for each of our electron configuration and orbital diagram, we're just going to add in 1 more electron. So our 2p is the next place that we can add an electron in. So instead of having 3, we're going to have 4. And the way that this changes our orbital diagram is that we're just adding in 1 more electron. So we're going to fill this one in down. And I usually just move left to right. So that would be our electron configuration and orbital diagram for oxygen. And then for nitrogen, not nitrogen, fluorine, I'm going to shrink these. Okay, so we're going to be working on fluorine here in the bottom left. So for fluorine, we've, again, just added 1 to this 8 electrons. If we look at a periodic table, you can also see that it's 9 electrons. So 9 electrons, we have to add 1. We can put that into P. So it's 2p5. And then that's reflected in our orbital diagram. We're going to add in 1 more electron. That's going to be another down. And then for our last one, for neon, neon has 10 electrons. Instead of being 2p5, it's going to be 2p6. And it's got all of its electrons filled in, all of its orbitals filled in. So you've got 1s2, 2s2, 2p6, so you've got lots of up and down combinations. And our neon is the end of row 2. You may see on the periodic table. It's all the way on the right in row 2. So it represents a full n equals 2 principal shell. So 2s is full, 2p is also full. So 2s2, 2p6. The reason that this is important and this is helpful is that you can imagine that if I said for you to take out your periodic table and write an electron configuration for bismuth, way down here, right, bismuth has 83 electrons. So imagine how much fun we would be having if we were filling in 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then other stuff after that, until we eventually get to a complete and full shell and orbital diagram for bismuth. We don't want to have to do that because that's way too much writing. And so the reason that I'm pointing out, that we're pointing out that this neon is the end of row 2 and it's a full n equals 2 principal shell, so we can use that as a shortcut. So any of our noble gases, those are the ones over in the far right column, our noble gases, any of those can be used as a shortcut. So any of these, helium, neon, argon, krypton, xenon, etc. We can use those, the symbol for that, in brackets. That'll symbolize everything that's included in the orbital diagram and electron configuration for that noble gas. So for sodium, we want to put the previous noble gas in brackets. So we find sodium on our row 3. It's the first entry in our row 3, it's Na. The previous noble gas is neon, and we just went over the electron configuration and orbital diagram for neon. So we can skip most of the work by just writing neon in brackets. All right, so we're working with sodium. It's got 11 electrons. How many electrons does neon have? Normally it has 10 electrons. So by putting the symbol for neon in brackets, we're taking away 10 electrons. We've got 1 electron to place after we write in that symbol. And our next place that we can put electrons is 3s. We only have one electron, so it's 3s1. And that's our entire electron configuration. Wasn't that easy? So previous noble gas in brackets, and that sums up everything up until that point. So the first two rows of electrons get summed up just by writing neon, Ne, in brackets. And we can do that for stuff that's lower on the periodic table as well. So this is a huge time saver. So for example, we can write these electron configurations. So for aluminum we find it's in row 3. So we're going to look for our noble gas in row 2, which is again neon. So aluminum, we've got 13 electrons. The previous noble gas is again neon. Neon has 10 electrons, so that takes 3 out. Sorry, it takes 10 out. We've got 3 left. Our next entry after neon, we're in row 3, and the S block is the first 2 columns. So 3s comes next. I'll talk about that more in depth, I think, soon. So 3s is our next energy level. When we have 3 electrons, we can only fit 2 into our 3s. So it's 3s2. After 3s comes 3p, and we would put our 1 remaining electron into 3p. For bromine, Br, bromine is in row 4. Argon is our previous noble gas. And bromine has 35 electrons. Our previous noble gas in brackets, Ar. Argon has 18 electrons. So we've got 17 electrons left to place. All right, I think I made an oopsie, an order oopsie. Okay, so this is where I was supposed to explain how we use the periodic table. So we're going back to it. Sorry about that. So the reason that these blocks are important, the order that electrons show up, or the order that elements show up in the periodic table, the order that they're in here tells us what order we fill in our different orbitals. So we start with number 1, hydrogen. Hydrogen is in the S block, and it's in row 1. And so we're filling in row 1, S block, we're filling in 1s. Helium's the weird one because it's like kind of out of sequence. For this, it should show up here. It's whatever. So we would fill in, helium is also in row 1. It counts as our S block, so we'd be filling in 1s. After helium comes lithium. It's next in our order. We're in now row 2. And we're in the S block, so we're filling in 2s when we're on lithium and beryllium. After beryllium, we jump across our D block. So we jump from beryllium to boron, which is our P block. So that's why on boron we're filling in 2p. We're in row 2 in the P block, so we're filling in 2p for these 6 elements. After 2p, after neon, we jump over to sodium. What row are we in? We're in row 3. So we're filling in 3 in the S block, so 3s for sodium, magnesium. After magnesium, we jump across to aluminum, still in row 3. So we're filling in 3, but we're in the P block, so this is 3p. Are we seeing how that works? So we're filling in 3p. And this is where the periodic table helps us to remember that the order is not what we would expect. Okay, so after 3p, go to 4s. And this is why we go to 4s. So from argon, argon's number 19. It's the end of our row 3 in the P block. After argon, we go to potassium. Potassium is in row 4. It's in the S block, so we're filling in 4S next. What comes after calcium, the end of our 4S? What's after calcium? What's the element? Or what's the block? It's the D block, right? So we go from calcium, which is in 4S, to the D block. Where does our D block show up for the first time? 3. So you may remember back, we had N number 1, 2, 3 subshells. This also shows up in the slides earlier. So in 1 we have S, in 2 we have S and P, in 3 we have S, P, and D. So our first entry into the D block is 3D. So this is the weird part, is that we're filling in, this is our first row of the D block, so it's 3D, even though it's in row 4. So our D block is always row minus 1. So that makes our D block a little bit weird, but if you remember that 3D is the first place that our D subshell, our D shapes show up, then hopefully you won't get that confused. Okay, so we move on from 4S into the 3D, and then we get back to, after zinc, our P block. And we're in row 4, so it's 4P. After 4P, we would move on to 5S, because it's row 5. So row 5 in our S block, we jump back into the D block. Again, we have to subtract 1 from the row number. So from strontium to yttrium, from 5S, we move to 4D. We're filling in our 4D as we move left to right across that block. After we finish out 4D, remember we're in row 5. We're in the P block, so it's 5P. So if you remember the row number, if you remember the block names, the letters that go with the blocks, that can help you with filling these in. It's also sort of a cheat sheet for filling in the electrons, electron configurations as well. Any questions at all about how we did any of that? If you are confused, if you have questions, if you're not sure, if you'd like more practice, you can go to our SI sessions, 3:30 to 5:30 in the steam room, not the sauna, the steam room, over in the library. Or you can ask me during lab or after lab or between lab and lecture or some other time, like office hours. Okay, so jumping back to electron configurations. So for bromine, we're past argon. So argon's our previous noble gas. That's why we wrote that symbol for argon, AR, in brackets. After argon, we're in row 4, and we are in the S block with potassium, K. So that's how we know that we are in 4S. So we're in row 4, S block. Are we past our 4S block, right? We are. We're in bromine, so we're past that. A full S subshell is 2, so 4S2. After 4S, after calcium, comes scandium. Scandium's our first entry in our transition metals block, our D block, and so that's going to be 3D. So it's row minus 1 because it's D block. And again, we're D block because transition metals block. Who remembers how many shapes we have in our D subshell, the double dumbbells? We have 5 shapes, 5 orbitals. We can fit a total of 10 electrons into 3D. The other way that we can remember this is if we count across our D block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10 wide. The block is 10 wide, so you can fit 10 electrons into your D block. Every element in that block counts for adding 1 electron in. So at the end of the D block, it's 10 wide, so 3D10. We're past our D block. So we know that it's going to be full D block. Then we get back into the P block. P block, row 4, doesn't say on our periodic table in class, but it's row 4. So 4P. And what spot are we in? Counting left to right, what spot are we in for number? 1 through 6. We're in the 5th spot, so 4P5. You don't have to do any math. You just have to do a little bit of counting and a little bit of remembering, like for the D block stuff. And that is the correct electron configuration for bromine. Any questions about that magic? To me, it feels kind of magical to do it that way. I love it. Okay, so go ahead and do an electron configuration for strontium. All right, strontium, Sr. Find it on the periodic table. That's the first step. We find Sr. It's in our S block. It's in row 1, 2, 3, 4, 5. Row 5. To abbreviate our electron configuration, we're going to go up a row and to our noble gas, which is Kr, krypton. So for strontium, we put Kr in brackets, and then we're picking up at the start of the next row. So krypton, moving over to our row 5. Row 5, we are in what block? S block. So our alkali and alkaline earth metals, that's our S block. Our P block is the far right 6. That kind of, it's almost square. It's maybe square. Looks square. And then our transition metals in the middle is our D block. F block, scary stuff, is below the periodic table. It's the like pulled out, cut out bit. So we're in our 5S. So row 5. That does not look like a 5 to me. There we go, 5. And we are in the S block. What entry in the S block are we? Are we the first spot or the second spot? We're in the second spot, so it's 5S2. It takes a little bit of time, maybe a lot of time, depending, to really master, get good at this method for doing electron configurations. Once you get it down, though, electron configurations are so easy. They're so easy, they're so fast, doesn't take a lot of brain power. It's pretty easy, too, on like exam information sheet, periodic table, to write in the rows. Just count 1 through however many rows you need, and to label your S, P, and D blocks if you need to do that too. And you might be thinking, what good is electron configurations? And you would be jumping the gun just like me, because we're going to do some more orbital diagrams first. We actually already did carbon, so I'm not going to do that one. So never mind. I didn't jump the gun, I just jumped my slides in the wrong order. Okay, so part of the reason that we're learning this, the reason that we're learning electron configurations and our periodic table, is to talk about valence electrons. Valence electrons are basically outside electrons. This is our outer shell of electrons. So if you remember from the Bohr model, we had the different like rings. N equals 1 was our most inside ring, then after that we had n equals 2, n equals 3, n equals 4, etc. We're basically thinking about those rings as shells of electrons. It also corresponds with our n numbers in the quantum mechanical theory. So our valence electrons are any of the electrons in that outermost principal shell, so whatever our highest n number is. And these are the ones that are involved in bonding. So valence electrons can engage in bonding. They can also be stolen. They can also be given away, depending on how you want to think about it. So it's those valence electrons on the outside that can be pulled off, or they can be linked up with other atoms to form bonds, which we're going to talk about more in this chapter. Everything that's not in those valence electrons, those outside electrons, is core electrons. So if we do an electron configuration, like this one for silicon, we've got the complete electron configuration. We didn't use any shortcuts here. So silicon has 1s2, 2s2, 2p6. That's all the way up through neon. We could have also abbreviated this as Ne in brackets. That would also work. And then if we look at where silicon is on our periodic table, we're in row 3. We're past 3s. We're past row 3 s block, sodium and magnesium. We are the second entry into the p block, also in row 3. So that's where we get the 3p2. So we count up, we add up these electrons in our 3, our n equals 3. We've got 4 total electrons there. So between our 3s and our 3p, we've got 4 electrons. And those are our valence electrons. Everything else, the stuff that gets lumped in with neon, is our core electrons. So those are not going to be able to engage in bonding, generally. Okay, so let's write an electron configuration for chlorine and identify our valence electrons, our outside electrons, and our core electrons. I'll give you a little bit of time to work on that. All right, electron configuration for chlorine. We're going to go ahead and do a full electron configuration because we know the secret. So our electron configuration for chlorine. Chlorine's in row 3, so we can just fill in row 1 and 2. In row 1, we've just got our s, so 1s. We've got 2 entries in 1s, so it's 1s2. Then we would go to row 2. In row 2, we encounter our s block first, lithium, beryllium. We are well past 2s, so we're going to fill it up 2s2. We are then moving on to our p block, also in row 2. We are past our p block in row 2. So 2p, we've got 6 elements wide in our p block, so it's 2p6. After 2p, we move on to row 3. In row 3, we've got our s block that comes up first. We are past our s block. We're over in our p block, so we can fill in 2 for our 3s because we're past it. And then we get, after we jump across past our transition metals, 3p, and chlorine is the second to last entry or the 5th entry. So aluminum, silicon, phosphorus, sulfur, chlorine is 5. So 3p, 5. That would be our complete electron configuration for chlorine. You could have also abbreviated the 1 and 2, the 1s, 2s, 2p. You could have abbreviated that as neon in brackets. And when we do this, this also nicely separates our valence electrons from our core electrons. So our valence electrons are going to be our outermost electrons, our n equals 3 electrons. So this is the outermost shell. if we're thinking of our Bohr model, or our biggest principal quantum number, n, in our quantum mechanical model. So we've got 7 valence electrons. Our core electrons is going to be everything else. So everything that's symbolized or abbreviated, if we use our noble gas in brackets, that's all of our core electrons. At least in this case. So our core electrons are everything else. There's valence, then there's core. Those are the two options. Something that's cool about valence electrons and the way that our periodic table is laid out is that elements in the same column have the same number of valence electrons. So this 1A, 2A, 3A, 4A, all those designations, the 2A means that we've got 2 valence electrons. The 3A, the 4A, all of those others mean exactly the same thing. We've got that number of valence electrons. If it's in this, whatever the column, it's got that number of valence electrons for those A designation names. So we've got 1 for our first column, 2 for our second column, skip our transition metals, 3, 4, 5, 6, 7, 8 valence electrons. They're all going to be very similar. We've got the valence electron configurations written out here. So the number of valence electrons for any of our main elements, that's the outermost electrons, the ones that can participate in bonding, is equal to the group number of its column. This is something that you will need to know. You need to know how to get the number of valence electrons. This is the fast and easy way, is just looking at what column is it in for our main group elements. The reason that you need to know this is because we're going to be using this, we're going to be building upon this idea, and then we're going to take that idea and we're going to build upon it, and then we're going to take that idea and build upon it, and I think that's all the building that we're going to do for this chapter. But it's quite a bit of building, and kind of the foundation of it is our valence electrons. So knowing our number of valence electrons. So again, for our main group elements, columns 1A through 8A, it's the same as the column number. So just skip the transition metal block, skip the D block, kind of in the middle there. And that's how you get the A designation numbering. The row number in the periodic table is going to be equal to the number of the highest principal shell, the n value, but for our D shell you subtract 1. For our F shell, if we were doing that, we would subtract 2. So the example that we saw earlier is that 3D shows up in row 4. For example. So you have to remember that our first row of our D block is 3D, not 4D. And here's a table that has, this is the electron configurations again. That's the one that we saw earlier where I was talking about the order that we fill up the electrons. So when we're in our transition metal series, our D block, we are mostly filling core orbitals, and the number of valence electrons is mostly constant. There's 2 weird exceptions in the first series because half-filled and completely filled D subshells are especially stable. So it's all about stability. And when we're in those first 2 rows, when we get to chromium and copper, we've got some weird exceptions. Usually they don't show up on exams, but I think they're interesting, so I'm going to talk about them a little bit. So we would expect, since we're in row 4, 4s, we're past 4s, so 4s2, and then our d block would be 3d4. And if we look at an orbital diagram for that, we've got our 4s and our 3d. That's what our orbital diagram would look like. So notice how we've got a paired up 4s, and our 3d, we've got 4 electrons that all have upspin. They're all in sync. It would be really, really nice if we had all 5 that were in sync. And that's actually what happens. So because of the spacing of these, or something along those lines, because of the way that it is, this down electron, this downspin electron actually gets filched, gets swooped up by our 3d, and so we get 3d5. So it's actually 4s1, 3d5, which I think is interesting. Good chance it doesn't show up on an exam, but I just think it's neat. And it's a similar idea for copper. So for copper, we would have the expectation for our 4s, so up, down. And then for our 3d, we've got our 5 boxes indicating 5 shapes. And we are just one short of a full d shell. And so a similar thing happens. The d orbitals swoop up one of those electrons. And so it's actually 4s1, 3d10, which is just weird and interesting. It doesn't really give us like any extra information or help us out really that much in this class. I just think it's neat, and so that's why I talk about it. Similar things can also happen for lower rows, but it's mostly in those rows. Here's a cheat sheet, a shortcut for filling an electron configuration. From the periodic table. So if you need like a visual guide to getting an electron configuration, then this might be your slide. It's the visual guide to filling in electron configurations from the periodic table. And that's more review. And if we wanted to, we could do this, use the periodic table to determine the electron configuration for As arsenic. So the first step would be arsenic. There's arsenic. What row is arsenic in? What row? 4. We're in row 4. What's the noble gas at the end of row 3? Argon. So symbol for argon in brackets. And then in row 4, what's the first block that we encounter? We encounter 4s, because our S block is our first 2 columns. We are past it, 4s2. We're past both of the entries. 2 entries, 4s2. And then we get to what block? Our D block. And our D block, our first row, is what? What number? 3. So this is our 3D. And we are also past 3D. So we would have 3D10. And then our last block that we get to here is what? What letter? P. It's our P block. And we are what number or what letter, what entry in this block? What column are we in? We're in the third column. So the third column of P block. And so we are row number 4. Our block is P, and we are the third entry, so 4P3. That's how we would put together an electron configuration for arsenic. Questions? All right, so one of the cool things about the quantum mechanical model is that the chemical properties of our elements is largely determined by the number of valence electrons they contain. So part of the reason we're focusing on valence electrons is because they have similar number of valence electrons in columns, and so they also have similar properties. That's part of the reason that we have a periodic table where it's like repeating patterns. So it helps us explain a bunch of things. For example, all of our halogens, atoms with 8 valence electrons, sorry, not halogens, noble gases. Noble gases, we've learned previously, are inert. They don't react. That's why you can do that fun party trick where you take a party balloon that's got helium in it, and you breathe in the helium, and then you talk, and your voice gets pitch shifted up. Because the helium is inert, it doesn't really react or interact with your body, so you don't have to worry about getting poisoned as long as the helium's clean. And it's low in energy, therefore stable, because it's got the full valence electrons. So for most of these, all of our electrons are paired up, and having all of your electrons paired up is really stable. This is also the reason that our examples are chromium and our copper from the transition metals block in the middle. Why those stole an electron from the S shell is because there's a lot of stability that comes from that. So our noble gases are really stable, therefore they're inert or non-reactive. Other elements, anthropomorphizing here a little bit. Other elements wish they were noble gases. What's another name for nobles? Royals. We all want to be royals. The elements also want to be royals. So elements that have electron configurations close to the noble gases are very reactive, most reactive, because they can get noble gas electron configuration. We've been looking at ground state electron configuration. So just the element out in the wild by itself, how many electrons is it going to have? If we have ions, we can add electrons and we can take away electrons. So you can get noble gas electron configurations by gaining or losing a small number of electrons. So we can add, remove electrons to get a full shell. For example, our alkali metals. The alkali metals are our first column on the periodic table, and they all have the outer electron configuration NS1, where N is their row number. So for example, for potassium's electron configuration, if we look at the previous noble gas, it's argon, and then it's row 4, because hydrogen's left off here for some reason. Who did that? So it's argon 4s1. So what we're saying is, on the outside shell, we just have the 4s1 electron. Inside of that, deep within every potassium, is an argon electron configuration. So we've got argon inside and 4s1 on the outside. What if we got rid of that 4s1. Now what's the electron configuration? It's just argon. So we've got a noble gas configuration just waiting, lurking underneath the surface. So if potassium loses one electron, then it attains noble gas configuration. If you lose one electron, electrons have a negative charge, so a 1+ charge forms if you lose one electron. And that's why all of our alkali metals form 1+ charges. That's something that we hopefully have memorized from previously because it showed up with like ions quiz stuff. So this is the reason why we get those 1+ charges for everything that's in column 1 or group 1. Our alkaline earth metals are just one column over, sorry. And so they all have 2 s electrons. So if they lose 2 electrons, they gain noble gas configuration. Noble gas electron configuration, which is especially stable. And that's indeed what happens. In reactions, they tend to form 2+ ions because of losing 2 electrons. So we're stripping away the outer shell, the outer valence electrons to unlock the noble gas configuration that's hiding underneath. Do we have any questions so far? And that's why they all form 2+ charges. The reason that our alkaline earth metals are less reactive is because they have to lose 2 electrons. It's harder to lose 2 electrons than it is to lose 1 electron. 1 electron, it's pretty easy. Like any time that pops off, then it gains that really stable electron configuration. For these alkaline earth metals, if they lose 1 electron, that gets them closer to their goal, but it's possible they could gain that electron back before they can get a chance to lose the other electron. And so it takes a little bit more action, a little bit more work to get there, but after losing 2 electrons, they can do it. Our halogens on our periodic table are all right next to our noble gases. And so if they were to move 1 spot over to the right, which would be gaining 1 electron, then they would have noble gas configuration. Just like it's easy to lose 1 electron, because you get rid of it and boom, now you're stable. If you gain 1 electron, boom, now you're stable. That's what our halogens are doing. If they gain 1 electron, they have noble gas configuration, which again is the goal for pretty much all of our elements, is this noble gas electron configuration. So for example, let's look at chlorine again. Chlorine's in row 3. So just looking at the outer parts, we've got 3s2 because we're past the s, and we are at 3p5. If it gains 1 electron, then it becomes 3s2, 3p6, which is the same as the electron configuration for argon. So if it gains 1 electron, moves 1 spot over to the right, then it becomes like a noble gas. It unlocks that extra level of stability, and it's especially stable, or as we often think of it, happy. And so that's why all of our halogens are especially reactive. They're so close to getting their dream, getting their wish, getting their goal of that noble gas electron configuration. So they're especially reactive. Again, these are the elements that form predictable ions. Other than zinc and silver, these are all explained pretty nicely and neatly by our... Actually, zinc and silver kind of work too, but whatever. These all kind of fit nicely into what we've been talking about. So for our 1A, if any of these loses one electron, like rubidium, rubidium then becomes like whatever would go into that box, krypton. So it's like a noble gas. For all of our halogens, if they gain one electron, then it's noble gas configuration. For all of our 6A group, our oxygen, our sulfur, our selenium, if they gain 2 electrons, if they move 2 spots to the right, then they get noble gas configuration. The same idea for our 5A, but for 3 spots over. So that's where all of those ions and ion predictions come from. And then I think we'll stop there because let's learn our first trend. Might as well. So there's some trends also on the periodic table. Our first trend is atomic size. Atomic size is the distance between the outermost electrons and the nucleus. For all of our trends, we are going to be thinking of them as left to right and top to bottom. So it's either increasing from left to right or it's increasing from right to left. It's increasing one of the directions left, right. It's increasing one of the directions up, down. We're going to start with the one that doesn't make as much sense at the face value. So if we move across a period or a row on our periodic table, right, we're moving left to right, you might expect the numbers are going up, and so we would expect the size to go up as well, which is not the case. So the size of our orbitals, the size of those shapes, we can think of like the sphere for our 1s, 2s, 3s, 4s, etc. The size of the sphere depends on the number. So 1s is small, 2s is bigger, 3s is bigger. The same thing is true for our other shapes. And that doesn't change when you move from left to right across the periodic table. So we're staying the same orbital size. We're working with the same sphere. But remember, that sphere is our electrons, where we are likely to find our electrons. As we go across a period, again, that's a row, the number of protons in our nucleus is increasing. So our positive charge at the center of our atom is increasing. And since our electrons are what make up that shell, that sphere shape, if we're increasing the positive charge in our nucleus in the center, thinking of it like this, if we increase that positive charge, we would expect that our electrons are going to get pulled in a little bit, just a little bit, because of the increased positive charge, so they're more attracted to the nucleus, and so that's going to bring them all a little bit closer in. So what actually happens is that from left to right on the periodic table, our atomic size decreases just a little bit because of that shrinkage from the increased positive charge at the center in our nucleus. The one that makes sense is top to bottom. So when we're moving down a column on our periodic table, so for example, looking at our first row, or our first column, hydrogen, lithium, sodium, potassium, we're adding shells of electron, so it's getting bigger. Adding shells / layers, so it increases in size. So for atomic size, this is our trend. I've got these both in terms of which way it increases. So it increases from right to left. Less protons in the nucleus means that the electrons aren't held as tightly, so our electron cloud can be a little bit further away. And then top to bottom, it increases because we're adding those layers on. And then next class, we'll pick up with making some guesses about atomic size.